Dunggan ako, dunggan ako.
Ah,
Oh. In this second example, we look at the impulse for an object that collides with a wall and bounces back after the collision. If a 2 kilogram object travels with a velocity of 10 meters per second before it hits the wall and a velocity of negative 10 meters per second after the collision, um, it is called negative because it bounces back in the opposite direction. So then the impulse can be calculated as follows. Um, Impulse equals to final. Um, they will have the same formula. So the if you say the formula, if the PF minus PI for final minus initial or MV final minus MV initial, it will be um, 2 kilograms times 10 meters per second minus 2 kilograms times 10 meters per second is equals to negative 20 kilograms meters per second minus 20 kilograms meters per second equals to negative 40 kilograms or meters per second. Um, and in this next example, we'll calculate impulse a different way. What is impulse? What is the impulse caused by an average force of 10 newtons if it acts on a ball for 2 seconds? The impulse here can be calculated as impulse times force. Impulse equals force times time multiplied by time. So the given nato is 10 newtons and ang 10 newtons if acts on a ball for 2 seconds. This is na i-times na ang force times time. Since ang force is 10 newtons, then ang time is 2 seconds, we will have 20 newtons per second. Thank you for listening and God bless.
Group 5, isa ang wala naka-report sa inyo.
naka-report tanan, sir.
At yung naman makabak na. Straight.
Yes, sir. Talurami.
Okay. So, any questions from the topic? Astrid, do you have more examples on how to apply impulse and momentum?
Mauna ko among na-prepare, sir.
Okay. So, Nikki, how much time left?
9 minutes and 5 seconds, sir.
Jay, kumusta naman Jay? Lagi na mo?
Okay, sir. Okay na lang naman, sir.
Lagi na mo? Okay. Sige, group 6.
Mauna ay group 2 na Christian.
Sige, balik siya sa group 2 no, yung question. Pwede na Nikki?
Yes, sir.
Sige. I-play na lang Nikki.
Excuse me, sir. Ang ilang video scan for viruses.
Nag-scan pa mo.
Excuse me sir, kuan ga-feedback imong pag-imong or karat.
How about this one, Gia? Okay na?
Yes sir, okay na.
Nikki,
Yes, sir.
ano sa ta, no? Sa group 6 sa ta?
Sige, sir.
Okay, sige, group 6, kamusta?
Good afternoon, classmates. Phoebe, makita ninyo?
Oh,
Ray.
Makita ninyo?
alright.
O,
Phoebe, start na. Makita nimo? Saba pa. Ray, makita ninyo?
Oray.
Si Phoebe.
Wala.
Wala.
Wala, ikaw na lang, Ray.
Naka-leave.
Sugdi na ray.
Oh my God. Wala siya ba?
Wala ray.
Oh my, di ka ba wala? Bit, ikaw, Rabi.
Naka-join na
Wala
siya.
yung signal. Naka-join na.
Fabi.
Wala ta na to.
Mag-start na ko.
Oo, sige, start na.
Good afternoon, everyone. Our topic is impulse momentum theorem. Impulse momentum theorem: when a net force acts on an object, the impulse of the net force equal to the change in momentum of the object. The impulse momentum theorem is logically equivalent to Newton's law of the first law. Momentum. Momentum is basically mass in motion. is a quantity that describes an object resistance to stopping a kind of moving inertia.
The quantity that
Momentum is represented by the symbol P. Momentum is also the product of mass and velocity, or momentum is equals to mass and velocity. Momentum is a vector quantity since velocity is a
is
vector and mass is a scalar. Impulse. Impulse is a quantity that describes the effect of a net force acting on an object, a kind of moving force. Impulse is represented by the symbol J. Impulse is also the product of average of net force acting on an object and its duration. The formula is impulse is equal to force times change of time. Impulse is a vector quantity since force is a vector and time is a
del
scalar. Impulse momentum theorem states that the change of momentum of an object is the impulse applied to it. If mass is constant, then force times change in time is equal to mass times change in velocity. If mass changing, then force times change of time is equal to mass times change of velocity plus velocity times change of mass. Mora to.
next.
Im-
Sige, sir,
Momentum
next ka na.
theorem equation. The impulse momentum theorem can be expressed like this: G equals delta P, where G is Newton seconds or kilogram meter per second. P is linear momentum in kilogram meter per second. Both are vector quantities. The impulse momentum theorem can also be written out using the equation for impulse and momentum like this: G equals Ft m delta Vf minus m delta Vi, where G is impulse in Newton seconds, m is mass in kilogram, final velocity minus initial velocity in meters per second. F is net force or newtons, and T is the time in seconds. Next slide, Ran. Units. The SI unit of impulse. The SI unit of impulse. These units of impulse and momentum are
Theorem.
equivalent to Newton second times kilogram meter per second. Concept of dynamics. First law, inertia, M. Momentum, P equals mass times velocity. Sa second law, fourth law, F equals mass times acceleration. Impulse momentum theorem, G equals delta P. Third law, reaction, positive F1 equation of momentum times equals sigma P. Next slide na.
Ryan, naka-on imong audio.
So impulse momentum theorem, it shows that the impulse of an object experiences during its collision in momentum in that same time. One of the most common uses is to solve for the average force of an object experiences in different collision. We have the derivation of the impulse momentum theorem. The impulse momentum theorem can be derived from the Newton's second law: force is equal to mass times acceleration, and rewriting acceleration as the change in velocity over time. And we have also the implication of the impulse momentum theorem. It states state that a major takeaway from the theorem is to explain how the force experienced of, by an object in a collision depends on the amount of time the collision takes. Next slide. So we have the example number one. Suppose that an emergency occurs on a space station and an astronaut needs to manually move a free floating 4,000 kilogram space capsule away from a docking area on Earth. The astronaut knows she can hold a 50 kilogram weight above herself for 3 seconds. How quickly could she get the capsule moving? So here are the solution. First, we calculate the total impulse that the astronaut can apply. They note that the astronaut is pushing vertically in both cases, so we don't need to keep track of the direction of the force. So we have the formula J is equal to mg time change of time. So simply substitute the value of the variables to the formula and we can get the 1471.5 Newton second. And by the impulse momentum theorem, we can find the velocity of the spacecraft. So 1471.5 Newton second over 4,000 kilogram and we can get the 0.3 meter per second.
Example number 2. Calculating momentum. A football player and a football. A. Calculate the momentum of a 110 kilogram football player running at 8 meter per second. B. Compare the player's momentum with the momentum of a 0.10 kilogram football thrown at a speed of 25 meter per second. Solution for A. Player is equal to 110 kilogram times 8 meter per second is equal to 880 kilogram meter per second. Solution for B. Linear momentum of ball is equal to 0.410 kilogram times 25 meter per second is equal to 10.25 kilogram meter per second. Example number 3. A volleyball is spiked so that its incoming velocity of positive 4.0 meter per second is changed to an outgoing velocity of negative 21 meter per second. The mass of the volleyball is 0.35 kilogram. What impulse does a player apply to the ball? Incoming velocity is positive 4.0 meter per second and outgoing velocity is negative 21 meter per second. Mass is 0.35 kilogram. Vector J is equal to delta of vector P is equal to mass times incoming velocity minus mass times outgoing velocity. I-substitute there 0.35 kilogram which is the mass and negative 21 meter per second minus 0.35 kilogram times positive 4.0 meter per second is equal to negative 8.75 Newton second. Thank you, Sir Morato.
Okay, so kana no, you have three problem solving examples. No? So any questions at tong mga sample problems? Nikki, how much time left?
3 minutes and 48 seconds, sir.
Okay, can we proceed to group 7? Group 7.
Yes, sir. Jonathan. Jonathan.
Ay wait lang. Mag-present na ko.
Yes, Tan.
Mm, mm. Dili sa mga istorya makay. Ay, sa present. Ay, hala.
Okay na? Ay, mag-start na ko?
Start na dan.
Sige, ang slide, Tan. Please. Okay na?
Okay na. Sorry kay guys kay delay gid siya kay akong laptop kay nagkuan ay system update.
Tan, mawala-wala ang slide. Okay na? Tan?
Istorya lang dan kay gina-off na ko ang mic. So, sugod na ta.
Tan,
Sugod na ta.
mag-start na ko?
Ah, i-off lang na ko
Wala
ang
na
mic
yung
kay
gating.
saba diri sa amo
Hello?
Danica, you can start now, according to Jonathan.
Dunggan ko.
Yes, Jonathan, we can
Tan,
hear you.
nawala ang slide.
Ay sa kay mag-off mic na lang dayon ko dan kay saba kay sa mo abay.
Okay, okay, Tan. Sige lang. Okay. So good afternoon, everyone. Good afternoon, sir. So for the group 7, we are assigned to discuss or to present or to report to the class the types of collision. So we are assigned a topic of types of collision. So before there are two types of collision. The first one is the elastic collision and the second one is the inelastic collision. So before nato isgutan ang unsa to nga mga type ug unsay meaning adto nga type, let us talk about first what is collision. So unsa day collision? So collision is the sudden, forceful coming together in direct contact of two bodies or objects. So whenever an object in motion comes into contact with another object, we can call this event a collision. So let's cite for an example when we bounce or magdribble ta og bola, when we hit the baseball or when we hit the baseball or when we play pool or billiard. So in any collision, linear momentum is conserved. And for the formula of collision, we have m sub 1 times v sub 1 is equal to m sub 2 is times v sub 2. So this is the example of the two types of collision, which is the elastic collision and the inelastic collision. And for the discussion of that examples, let me call on my co-reporters. Thank you.
So, good afternoon once again. So, the first type of collision is elastic collision. So, it is a collision in which there is no net loss in kinetic energy in the system as a result of the collision. So, both momentum and kinetic energy are conserved quantities in elastic collisions. So, suppose two similar are traveling toward each other with equal speed. So, sa may example ani, so, example ani is kaning sa billiard. So, ang billiard, so when a ball at a billiard table hits another ball, so it is an example of elastic collision. So, the second type of collision is in elastic collision. Jisabel.
So the inelastic collision is an elastic collision. An inelastic collision is a collision in which there is a loss of kinetic energy, while momentum of the system is conserved in an elastic collision. Kinetic energy is not. This is because some kinetic energy had been transferred to something else. Thermal energy, sound energy, and material deformation are likely culprits. So here are some examples of inelastic collisions. Formula. So the formula is m sub 1 v sub 1 I plus m sub 2 v sub 2 I is equal to close and open parenthesis m sub 1 plus m sub 2 v sub f. So m sub 1 stands for mass on object 1. V sub 1 I stands for initial velocity object 1. M sub 2 stands for mass object 2. V sub 2 I is initial velocity object 2. V sub f is final velocity of the objects. So the example of inelastic energy is kanang kung magbangga ang kanang example madisgrasya magbangga ang two objects. So mara to sir.
Group 7, do you have examples, problem solving examples? Danica? Okay, let's proceed to group A.
Yes, sir. conservation of total linear. So good afternoon everyone. For this afternoon, we're going to report the topic about conservation of total linear momentum. What is momentum? The momentum is stored force which contains by the body in its state of motion. The conservation of momentum states that there is no change in total momentum of system during any change in the system. The body maintains its constant value. Thus, we can say that the momentum of a moving body retains its momentum constant without any external force. It can also be conserved by changing one form of momentum to another form, the momentum related to mass and velocity of the object. Principle of conservation of linear momentum. The conservation of linear momentum
Sir, muna na ang pinakakusog sa video nila, sir.
Okay, sige. Please continue.
is based on the principle of Newton's first law of motion. It implies that for an isolated system, for a system with no external force, the momentum remains a constant quantity. It also implies the Newton third law of motion, the law of reciprocal action, which states that the force acting between systems is opposite in sign and equal to each other. Law of conservation of linear momentum. All the bodies have the power of exerting a force on other bodies that are in their line of motion. The magnitude or quantity that measures this capacity of the body is called linear momentum. The law of conservation of linear momentum states that the momentum will remain constant no matter what until and unless any external force comes into action. This results into the fact that the center of mass of the system of objects will move with the same or constant velocity unless and until it is being acted upon by external force. The conservation of momentum is mathematically the result of the homogeneity of space. Conservation of momentum implies that the physical laws are independent of the position. When a gun fired, if we assume that the initial position was at rest and hence the initial momentum to be zero, the final momentum should also be zero, according to the law of conservation of momentum. So, second, let us suppose the file cabinet is in the middle of the room. A room with a smooth floor. We give it a push. In order to move it close the wall and before we realize it slams into the wall. It is difficult to stop because it has linear momentum.
Conservation of linear momentum equation. For two objects with initial masses of m1 and m2 and initial velocity of u sub 1 and u sub 2 with final velocities after collision v1 and v2, we can write the law as m sub 1 u sub 1 plus m sub 2 u sub 2 equals m sub 1 v sub 1 plus m sub 2 v sub 2. The momentum remain conserved. The momentum that is lost initially is equal to momentum gained afterward. The vector sum of all the given momenta for closed system with no external force acting on it remains constant. P sub 1, P sub 2, P sub 3, P sub 4 plus P sub I equals K, where K is constant. Also, linear momentum of a system of particles for a system of particles with a mass of m1, m2, m3, and so on. The linear momentum can be expressed as P equals mv equals m sub 1 v sub 1 plus m sub 2 v sub 2 plus m3 m sub 3 v sub 3 plus m sub 4 v sub 4 plus so on plus m sub I v sub I for the object with initial masses of m1 and m2 and initial velocity of u1 and u2 with final velocities after collision to be v1 and v2. We can write the law as m sub 1 u sub 1 plus m sub 2 u sub 2 equals m sub 1 v sub 1 plus m sub 2 v sub 2. Also, angle p sub 1 equals negative angle p sub 2. P, the product of mass and the velocity of particles. P equals Vm. Magnitude. P equals mv or P to the power of 2 equals m to the power of 2. V to the power of 2 equals 2m times 1 half mv to the power of 2 equals 2 mk. Thus, P equals square root of 2 km. K equals P to the power of 2 divided 2m. Here, K equals kinetic energy. According to Newton's second law, F equals ma equals m dv divided dt equals d times mv divided dt equals dp divided dt. Thus, F equals dp divided dt. Considering external force on the particles or a body equals 0, we have F equals dp divided dt equals 0. The law may be extended to a system of particles or to the center of mass of a system of particles. For example, for system particles, if net force or the vector sum of all the force on system of particles equals 0, the vector sum of linear momentum of a particle remains conserved. If F1 plus F2 plus F3 plus so on plus Fn equals 0, then P1 plus P2 plus P3 plus so on plus Pn equals constant. The same is the case for the center of mass. Fcm equals 0. Pcm equals constant.
Conservation of momentum in two dimensions. Conservation of momentum in all closed systems is valid, regardless of the directions of the objects before and after they collide. Most objects are not confined to a single line, like trains or rail. Rather, many objects, like billiard or balls or cars, can move in two dimensions. Conservation of momentum for these objects can also be calculated. Momentum is a vector, and collisions of objects in two dimensions can be represented by axial vector components. Conservation of linear momentum is also possible in two dimensions by calculating the component of momentum in different axes like x, y, and z. Also, the component of velocity should be calculated in all axes. Here is an example problem of conservation of total linear momentum. A 2,250 kg pickup has a velocity of 25 ms to the s. What is the momentum of the truck? Momentum equals 2,250 kg times 25 ms, or the velocity. It is equals 56,250 kj/ms to the s.
Example number 2. So sa example number 2 natin duha ka kaliton. Ang unang nga kaliton is 30 kilogram with a speed of 2.0 meter per second. Ang ikaduha nga kaliton is 22 kilogram. So sa ani nga problem ang atong pangitan is ang V sub 2. So sa pagkuha sa V sub 2, ang atong formula nga gamiton is M sub 1 times V sub 1 equals M sub 2 times V sub 2. P equals MV. P equals ang value sa M sub 1 is 30 kilogram times then sa V sub 1 nga 2.0 meter per second. So mukha na to din ang P equals 60 kilogram meter per second. 30 kilogram times plus 2.0 meter per second equals 22 kilogram times V2. So para mukha na to ang V2 equals plus 2.73 meter per second, times lang ang 30 kilogram o ang plus 2.0 meter per second i-divide sa 22 kilogram.
Okay, group 8. Nikki, can we have again the video of group 2?
Yes, sir.
Afternoon, classmate. So today our topic is all about kinetic energy, rotational. So what is rotational kinetic energy? Rotational energy occurs due to the object's rotation at it and is a part of its total kinetic energy. If the rotational energy is considered separately across an object's axis of rotational, the moment of inertia is observed. Rotational kinetic energy is directly proportional to the rotational inertia and the square of the magnitude of the angular velocity. A rolling object has both translational and rotational kinetic energy. Rotational kinetic energy formula. So PR equals 1/2 and the inertia is W2, where KR is rotational kinetic energy and I is the moment of inertia and W is the angular velocity. According to Newton's second law, the acceleration is equivalent to the resultant's velocity divided by the time, and average velocity is half of the final velocity. In rotational case, the angular acceleration given to the wheel is fetched from Newton's second law of rotation. The mechanical work that is required during rotation is the number of torque of the rotation angle. The axis of rotation for an attached object is mostly around its center of mass.
Rotational kinetic energy derivation. For any object to rotate such as grindstone or merry-go-rounds, work must be done. Consider a situation where work is done resulting in a rotational situation such that the net force exerted is perpendicular to the radius of the disk and continues to remain perpendicular as the disk starts to rotate. The net work done is the product of force times the arc length traveled, since force is parallel to the displacement, which is given as net work equals net force times second. By multiplying and dividing the above equation with the radius, we get quantities related to rotational quantities, which is net work is equal to radius net force times square as second over radius. From the above equation, we understand that Radius net force is equal to net and second over radius equals theta. Therefore, net work is equal to net times theta. The above equation is the expression for rotational work. To obtain an expression for rotational kinetic energy, let net is equal to moment of inertia. Therefore, net work is equal to moment of inertia. The net work done is given as net force delta second. Since net force on the disk is perpendicular to the radius of the disk as the disk is rotating because of the force. From rotational kinematics equation, we get work squared is equal to work squared times 2. Net work equals 1 half moment of inertia work second equals 1 half moment of inertia work second. The above equation is the work energy theorem. For rotational motion, we can define 1 half moment of inertia work second to be rotational kinetic energy for an object with moment of inertia and angular velocity from the analogy with translational motion. Therefore, rotational kinetic energy is equal to 1 half moment of inertia angular velocity 2. So rotational kinetic energy example problems. So the question is, a round grindstone with a moment of inertia 1,600 kilogram meter squared is rotating at an angular velocity of 6 radians second to the power of negative 1. What is grindstone's rotational kinetic energy? So the given is moment of inertia is 1,600 kilogram meter squared. Angular velocity is equal to 6 radians squared to the power of negative 1. From rotational kinetic energy formula, Kr is equals to 1 half times 1,600 kilogram meter squared times 6 radians squared raised to the power of negative 1 squared. So Kr is equal to 1 half times 1,600 kilogram meter squared times 36 s raised to the power of negative 2. So you might be asking why it became 36 seconds raised to the power of negative 2, since the formula above is saying to square the 6 radians. So 6 radians squared is 36. So that's why Kr is equal to 1 half times 57,600 kilogram meter squared second times second raised to the power of negative 2. So in this point, we multiply the 1,600 kilogram meter squared and the 36 second raised to the power of negative 2. So we get the 57,600 kilogram meter squared times second raised to the power of negative 2. So the answer will be equals 28,800 kilogram meter squared times square a second raised to the power of 2. So the answer is 28,800 joule. Therefore, the rotational kinetic energy of the grindstone is 28,800 joule.
Calculating helicopter energies. A typical small rescue helicopter has 4 blades. Each is 4 meters long and has a mass of 50.0 kg. The blades can be
approximated as thin rods that rotate about one end of an axis perpendicular to their length. The helicopter has a total loaded mass of 1,000 kilograms. Calculate the rotational kinetic energy in the blades when they rotate at 300 rmp. B. Calculate the translation kinetic energy of the helicopter when it falls at 20.0 meter per second and compare it with the rotational energy in the blade. Solution. Letter A, the rotational kinetic energy is, so mao ni siya ang formula. We must convert the angular velocity to radians per second and calculate the moment of inertia before we can find k. The angular velocity is, so ang 300 nga revolution aton i-convert into 1 minute. Ang 2 radian i-convert nato into 1 revolution. Ang 1 minute i-convert nato into 60 second. So equals 31.4. Ang radian i-convert nato into second. The moment of inertia of one blade is that of an thin rod rotated about its end. So naa dito sa listed in figure 10. 4 times 50.0 kilogram 4 meter square divided by 3 equals 1,067 kilogram squared meter. Entering angular velocity and rotational inertia into the expression for rotational kinetic energy gives kinetic energy 0.5 1,067 kilogram squared meter 31.4 radian per second equals to 5.26 times 10 raised to the power of 5 joules. Letter B, entering the given values into the equation for translation kinetic energy, we obtain kinetic energy, mass in kilogram, velocity in meter per second squared. 0.5 1,000.0 kilogram 20.0 meter per second squared is equal to 2 times 10 raised to the power of 5 joule. To compare kinetic energies, we take the ratio of translation kinetic energy to rotational kinetic energy. This ratio is 2 times 10 raised to the power of 5 joule divided by 5.26 times 10 raised to the power of 5 joule is equal to 0.380. Significance. The ratio of translation energy to rotational kinetic energy is only 0.380. This ratio tells us the most of the kinetic energy of the helicopter is in its spinning blades.
And that would be all. Thank you.
Jay.
Thank you. Thank you, sir. Thank you, class. Sorry for too much delay.
Okay, Jay, nalang ko'y gamayng ano no, clarification. You were referring to work sa katong inyuhang topic. Now, katong imong gina-refer nga work,
Angular velocity, sir.
yeah, angular velocity to siya, dili to siya gyud W. It's actually small letter omega, no? Greek letter omega, which means angular velocity or angular speed. So,
Yes, sir.
ano lang no, clarification lang kay you you might have misinterpret siguro no ang katumurag W where in fact ano to siya, ano to siya ang gi-present as example no sa last ninyo nga parts inyong video nag-present mo example, so sakto to sa pagkagamit dito pero ano lang, basig ma-misinterpret lang siya ng work. Well, in fact, it's actually angular velocity. Okay?
Okay, sir. Thank you, Nikki. Thank you, Nikki. Thank you so much.
So you still have time to revise or improve your PowerPoint slides if necessary. No, kana lang inyong i-clarify ang mga symbols na inyong gigamit para dili siya ma-misunderstood or ma-misinterpret sa inyong classmates. No? We have to be careful with the formula, with the symbols, with the values that you are presenting. So, nga na siya. Okay? So, ito lang topics like kulang ang problem-solving examples, you still have time to add problem-solving examples sa inyong PowerPoint. I think that's the case with sa inyo no sa group 5 and sa group 7. So dugangi lang ninyo og more samples, examples for your classmates to follow. Nakuha ninyo groups 5 and 7, okay lang?
Yes,
Yes,
sir.
sir. Okay, kayo.
Okay, so we still have one last batch of reporters. Sa next week na lang, no? Sa Monday. We still have time to meet on Monday. Nikki?
Next meeting, sir, group 8 and group 9 and group 10, rin mag-report.
Oh, group 9 and 10, and then please check the list be para dili ta masayo.
Sir, napay next topic for group 1 to group 4.
Napay murag ikog-ikog, no? Last na lang gyud. Starting with buoyancy, fluid flow, Bernoulli's equation, and viscosity. So 6 topics more next week. Pwede nato ni ano ho no la rason na tanan. Okay ra sa inyong class? Like
Next meeting, sir.
Yes, next meeting. Para ning atong gibuhat karon no, kaya ra man nato nga straight 5 topics, no? And then we still have time for your quiz. So sige. So, ang reporters karon, I hope na ready na inyong quiz for you to conduct your quiz through G-Forms link. But you have to I have to remind you about my atong editor's link. I'm checking my inbox from time to time. Gamay raman ang send sa ilang inbox sa ilahang link. So reminder lang no, so that we can review your test items, your quiz. And then atong humana og hatag og quiz, please coordinate with our class secretary, Nikki, para ma-come up na mo og atong summary of your results. No? So makita nato karon kinsa tong grupo nga nagtrabaho gid sa ilang quiz, gi-check gid nila, gi-compile, gi-record, no? Ana. And then you have to send that to the G drive. Ang drive na to ana kung asa nang i-submit. Okay ra class? So Nikki,
Yes.
paki-monitor ko Nikki ha.
Yes, sir.
Okay, so this week also, I hope no everybody nakapasa na mo sa inyong chapter 4. And then this coming Sunday, ang chapter 5 na po conclusion. So as you can see class, no, hapit na kita mahuman, ato man siyang by week. Weekly ang atong submission sa ato ang technical paper. So ato siyang gibahin-bahin para doable gid siya. No? So by the way, no, I also posted videos on research paper writing. Ano to siya, kang Dr. Sara Namoko to siya, no? From USTP. So I think you're familiar where is USTP. So ang ilang eskwelahan, mapod sila in by Science and Technology po na program. So Okay? So, i-check ninyo tong tutorial videos para makagain mo og kaning insights on how to improve your research paper. Okay? So group leaders, ready na mo sa inyong quiz. Ang inyong link i-post lang dito sa ang group chat, no? And then I'm going to check to monitor the group chat. So kung kinsa tong group nga nag-post na sa ilahang quiz. Okay ra class? Nakuha ra ninyo?
Yes, sir. Yes, sir.
Okay, so dito na lang ta mag-monitor no sa inyong quiz items. But don't forget no to send me first your editor's link by adding me or ako ang bukso email as one of your collaborators. No? Okay, so again, no, congratulations to the reporters for this afternoon na nahuman na gid ninyo no despite na just this afternoon nag-brown out yun. So I was thinking saan na sad ni karon no. So it's good na nibalik ra pod ang kuryente dayon and nahuman na gid nato ang ato ang task for this afternoon. This is the reporting. So class, any other concern before we dismiss? Okay na ba ang tanan? Jay, okay na ka Jay?
Yes, sir.
Gia, kung na may concern no, regarding your technical paper, mag-post lang mo questions, queries dito sa group chat para makita sa tanan. Okay, but so far so good. You were able to submit the chapters from time to time on a weekly basis, no? So, pag weekly basis gani ang ato ang submission, mas daghan, mas klaro din nga naatay ma-accomplish kaysa kadtong bulto-bulto, buo-buo, pag sa kabulan, binulan. Ang uban gani kay nagsugod sila sa January, then next time na magkita ay May na or something ana. So that is dili kayo effective, no? Compare aning ato ang style karon nga by weekly ang atong pag-submit. I hope okay lang mo no sa Sunday nato ginaset ang ato ang submission na weekdays pag yun, no? So okay class, ano na lang. Dito na lang ta sa GC nato, group chat nato makita. And then don't forget no sa katong akong gi-post sa G Classroom, tanaw to ninyo, watch the videos, and then leave your comments no sa ubos para ibawa na ako kinsa tong nagtan-aw gid nagsubay sa katos nga videos. Okay class, so see you next meeting for the last last batch of reporting. And then good luck sa inyong quizzes and also sa inyong chapter 5 technical paper writing. I-enjoy lang gid ninyo ang inyong ginabuhat. And then kung na may question, pag-post lang gid mo sa ato ang group chat. Okay, goodbye class. Stay safe and God bless.
Bye, sir. Thank
Bye,
you.
sir. Thank
Bye,
you.
sir. Thank you.
Thank you.
Thank you, Nikki. Thank you, Nikki.
Welcome.